Hello, and welcome to this video tutorial by OpenTopography. My name is Chelsea Scott, and today I will answer the question, should I perform vertical or 3D topographic differencing? So I'll begin by discussing what vertical and 3D differencing are. So this is vertical differencing, and we're looking at Yosemite National Park in California. And here in the gray images, you see two different topographic hillshades that represent Yosemite National Park at different time periods. And then the color map shows the topographic change. And in particular, where we see the red, this represents a rockfall and subsequent loss of vegetation in an area. And often in topographic differencing results, especially here, the red represents negative change of the Earth's surface. So here we see the loss of vegetation and the rock during the rockfall. White represents no change, and blue represents an increase in elevation of the Earth's surface. And the blue here represents a growth in vegetation between the two LiDAR acquisitions. So vertical topographic differencing is done with two data sets acquired at different times. And here we're looking at an example with LiDAR data. So the data set acquired before the event is called the pre or compare. And the data set acquired after is the post or reference. And here we see 2-point cloud data sets. And that's shown here, and as often the case, the later data set has higher resolution as well as lower error, representing the increase in the quality of LiDAR over time. So we take both of these point cloud data sets and we grid them to identical grids, so with the same bounding box and resolution. And the next step is to perform subtraction, specifically raster subtraction, where the difference is the reference minus compare, or the post minus pre. And that's shown here, where again, red is down and blue is up. And the resolution of the differencing is often at the meter scale. Specifically, it's at the exact resolution of whatever resolution the point cloud data sets are graded to. This is looking at 3D topographic differencing, where the arrows along with the colored dot represent the 3D change. Specifically, the arrow is the horizontal change, along with an ellipse representing the error in the horizontal change. And the colored dot represents the vertical change. The 3D differencing is computed using the iterative closest point algorithm. And this works by taking a windowed subset, often tens of meters long, of both the pre and the post-event point cloud, and then iteratively aligning those two data sets. Here we see the blue shifting towards the red. And we can shift and align these data sets using a rigid deformation. So this specifically includes a rotation and a translation. And it's important to note that the resolution of the differencing is often decameter scale, and that's because we need enough area to have sufficient features to align the 2-point cloud data sets well. So this 3D differencing has substantially lower resolution than the vertical differencing. So the key question for today, should I perform vertical or 3D differencing? In the short summaries, mostly vertical. And in particular, you should apply vertical differencing when the change is mostly vertical. So this includes looking along rivers, along coastlines for earthquakes, landslide, cliff collapse, volcanic eruptions, urban growth, and forest changes. But I actually recommend always starting with vertical differencing because this gives you an opportunity to really look at and better understand the error in the differencing results. And 3D differencing applies when the landscape shifts laterally. For example, tectonic fault motion, largely from a strike-slip fault, a creeping landslide, or sand dune migration. 3D differencing applies more when there is larger horizontal change. But it's important to note that these applications are fairly niched and really require that the landscape shifts laterally and maintains its shape. So here's some examples where it would make sense to apply vertical differencing. So here we're looking at Philadelphia in 2007 and 2022. And in red, we see a loss of a building, which was right here. And then blue shows new buildings that were built between the two LiDAR acquisition. And this is really a case where vertical differencing is the correct type to see the change in vertical elevation from either new or removed infrastructure. This is another example. This is looking at rivers in eastern Iowa, and vertical differencing is really useful for looking at erosion and deposition. Again, erosion in red and deposition in blue. And here we can also see quite prominent flight line errors. For example, here shown by the black arrow, and here shown by the other black arrow, and that there is a net downward change where the whole image kind of looks red, and we have a georeferencing error of about 0.15 meters in this image. And just to zoom in to let you better see some of those erosion and depositional signals. So for 3D differencing, I highly recommend always beginning with vertical differencing, as this lets you learn about the errors in your data set. So here we're looking at the Sumgullion landslide in Colorado, and here is the vertical change map of the digital terrain model. And in particular, you can see two different errors. First, along this north-south oriented stripes, we see some topographically correlated signals. And so we would expect to have larger horizontal alignment errors here that are consistent in sign. And here we also see these short scale slope dependent errors, which are due to geometric distortion. And so here are the 3D topographic differencing results. Specifically here, looking at this area, and they do look quite good, but we should, if we're interested in looking at this further, go back and look where that specifically that north-south stripe is. Think about how those georeferencing errors reflect the inferred change here. So this is looking at the sand dunes in New Mexico, and this is the topographic hillshade, as well as the change map, looking at vertical change. And so we see two error types. Again, these northeast and southwest flight line errors that are highlighted by the arrow, as well as a red background color, which also suggests a persistent georeferencing error. And specifically for this georeferencing error, we should understand that this error, which is quite prominent here, is going to appear in the 3D differencing results as well. But we can better see those errors here at the higher spatial resolution. And so when we would be looking at interpreting those 3D differences, we should just keep in mind that this vertical error is likely there. And so here are the sand dunes. Again, they shift laterally towards the northeast, which you could hypothesize based on the shape of the sand dunes. And in the vertical results from the 3D change, recall that there is going to be this net downward change due to this georeferencing error, as well as flight line stripes, that we should remember when we are interpreting the 3D differencing results. If you'd like to check out more, I recommend that you look at this paper written by the OpenTopography team in Geosphere, and it is open access. It's measuring change at our surface, on-demand vertical and three-dimensional topographic differencing implemented in OpenTopography. And to summarize, vertical or 3D differencing For most cases, vertical differencing is most appropriate, and you should always start with vertical differencing. For 3D differencing, this method really only works when the landscape shifts laterally, and the vertical differencing results are important for assessing the errors in the 3D differencing results.